So the next logical step beyond answering the question, how do you make an array, is to talk about how to make a 2D array and how to extend further beyond that. In this lecture, we'll discuss not only how to make a 2D array, but different implementations of arrays. Since 1D arrays use pointers, it only makes sense that 2D arrays will use them as well. This means that we must deal with dynamic allocation, except for this time it gets even more complicated. So like before, we'll need to define the size of our array. We'll do it with rows and columns because we're doing something 2D. This is the allocation first step. We create what looks like a double pointer, and we set it equal to something stored on the heap, an array of type integer pointer. So that means, on our little stack chart, we start with our double pointer x, which points to these pointers right here on the heap. That's the new int pointer of size num rows 4. Beyond that, we need to populate each of these pointers now. Because they are dynamic memory, we need to tell the compiler to make even more space on the heap for them. So we're saying every element of this array x is now going to hold a new set of integers of size num columns, or 5. And this is what we get. Each element of our first array of integer pointers now holds an array of integers, giving us this 2D look.
Does it matter which dimension represents the rows or columns?
Just like in most other languages, the implementation of a 2D array is totally up to you. If you want to make the first index rows and the second index columns, or the other way around, it doesn't matter, as long as you stay consistent. If we give you a problem involving a structure like this, we will have to tell you which way we're defining it. But, like with the first array, we must populate these elements, because they all start as either default or garbage values. So we have what we did on the previous slide, our allocated space. Now it's time to fill that space. I just want to make a nice, neat row of numbers, so it starts 0, 1, 2, 3, 4, all the way down to 19. And that's going to look like this. So below that we have our print method defined to show what we've done, but we're setting the row-column combination equal to the row times the number of columns plus the current column position. Which means when we call the print on each row, we get this output. It's great that we know how to populate a 2D array, but we need to know how to use them for certain functions. Here's what we have before, as well as our defined print method, but now what I'm going to do is create a new one-dimensional array. My goal is to swap one of these rows. So what we've done here is created an integer pointer y, and given it space equal to the number of columns in a typical row in the array I created. And now the values of this are going to be the index times 2. Now my goal is to replace the second row of this 2D array with what y points to. My first step is to delete what x1 points to. This way we don't have any memory leaks. Then I'm going to switch x1 to point to what y points to. Now that row appears in the array, but we have two handles on it. So I'm going to remove y from that position by setting its pointer value equal to null. This allows me to have control of this row just under the index of x, and no external source. When I print, it's going to look like this. So as you can see, we've successfully replaced one of the rows with a new one. As you can imagine, just as the allocation of a 2D array is more complicated than that of a 1D array, so is the deallocation. When you deallocate a structure like this, you kind of have to work backwards. This means that because we created the columns last, we have to start by deleting everything that the first dimension of the array points to. We've freed up all of the little subarrays, so now all we're left with is a bunch of pointers that are pointing to values we no longer own, which means it is good form to free them up. Then what we have to do is delete what x points to, and notice in both cases we've used that bracket syntax, which means we're telling the compiler to not just delete the one item, but free up the entire array. So I've shown you one implementation of this int double pointer x, the 2D array. But the thing is, there are actually at least 4. So the next one we'll talk about is a pointer to a pointer, and that's kind of the obvious one. So we create a pointer of type integer pointer on the stack, have it point to an integer pointer on the heap, and then have that pointer point to an integer that's on the heap as well. This isn't that useful, and you won't see it that often. The next one is a pointer to an array. So what that looks like is we create a pointer of type integer pointer, which then points to an integer pointer, and that integer pointer points to an array. So it's as if we've got a handle on the handle to an array. This is slightly more useful than what we showed you in number 2. And the final thing you may have is just an array of pointers. So this time, our pointer of type integer pointer points to an array of integer pointers, and then each of these integer pointers points to a single value.
How can I know which method will properly delete a double pointer?
Right, so each of these structures does get deleted in a different way. I can't just show you what we have in the middle there, an integer double pointer x, and tell you to free up whatever's associated with it. I need to either show you how I initialize it, tell you what it is, or something. Because with the bracket syntax, there's a different way of fully freeing it up. So if you were ever asked to free something like that up, we'd have to give you more to look at. The best rule of thumb is to know your implementation. Every time you create something new, you have to delete it. So if we look at the first example there, each of those rows was created with that new syntax, which means we have to go through and delete all of them. And then that initial array of integer pointers was also created with a new syntax, so then we have to delete that array. Now all of these implementations have different uses, and you'll find the ones that work for you. The most common is the 2D array, and that's why we like to focus on it, but know that all of these things are possible. With pointers, there's so much you can do, but you need to understand what you're doing.